Hi, in this video we are going to talk about Riemann sums. We are interested in finding the area under a curve. Like we have a graph of a function here. Let's call that y equals f of x. So this is the x-axis and the y-axis, and we pick two values of x, a and b, and we want to find the area enclosed in this region. So in this red region we want to find the area, and we cannot tell just by looking what the area would be. So what we want to do is we want to divide this region into several small rectangles, and we know what the areas of the rectangles are, and we would use that information to approximate the area of this region. So let's look at an example. So here is a graph of y equals x squared. So we want to find the area under y equals x squared between x equals 0 and x equals 2. So squared between x equals 0 and x equals 2. So one way to do it, so we have already divided this this area into four regions, four intervals. So it's 0 to 1 half, 1 half to 1, 1 to 3 halves, and 3 halves to 2. So one way to do this would be to draw rectangles like this to approximate. Like this. So this gives us an approximation which is called the left approximation, using not left, right. Sorry. So these are called the right rectangles because you are taking the value of y at x which is to the right of the interval. So when you look at this interval, the value to the right is x equals 1 half, and here you are taking the value of y at x equals 1 half, which is 1/4, and so on for each of these intervals. So we could also do the following. We could take the left values, which means we could take here, we could take the value x at x equals 0. Here we can take the value at x equals 1 half, here at x equals 1, and here at x equals 3 halves. So we will get this picture, and then the sum of these areas would be this green region, which is less, in this case this is less than the area we want to compute or we want to approximate. And in the right case we get this whole red region, which is more than the area we want to approximate. So here in the right case we have the area that we approximated is f of, not f, we call this is 1 half, so it's 1 half squared plus 1 squared plus 3 half squared plus 2 squared, and the whole thing divided and multiplied with the size, with the length of this interval, which is 1 half. And we can calculate this and get an answer which will be an approximation for the area. And for the other one, for the left approximation, we get left we would get let's start with 0, and then we get 1 half squared and then 1 squared, and then 3 half squared, and the whole thing multiplied by 1/2. That's the other approximation. Okay, and but note that if so here the right approximation is greater than the left approximation, but in this case where the graph looks like this, we would have a different story. So let's again consider the right approximation. Here it would be like this, then like this, then like this, and this. Yeah, and for the green or the left one we get like here, and then here, then here, then here. So now the green area is much bigger. So what I'm trying to say is that whether you get an overestimate or an underestimate depends on the behavior of the graph. We will continue in the next video.